Hi there, everyone. Welcome back. We are moving on with dynamics. Our next topic that we're going to look at today is something called apparent weight. And so apparent weight sometimes comes up in physics in the form of what we call elevator problems, which really, if you think about an elevator, is just a machine that's going to accelerate you upwards or downwards. And during that time, it might change how you feel. And you might have had this experience on an elevator or a roller coaster or even driving in your car if you go down a hill or over the top of a hill. Sometimes you feel like you're lifting out of your seat, almost like you're extra light. And sometimes you feel like you're being squished down into your seat, like you're extra heavy. The thing to realize about that is, of course, how heavy you are really just depends on the force of gravity. So that has to do with an attraction between you and the planet. How heavy you are isn't really changing. So what we say is the actual weight, which is gravity, is going to basically stay constant as long as you're around the surface of the Earth. But your apparent weight is going to differ. Now, how heavy you feel, or your apparent weight, is not the force of gravity. It's actually how much supporting force is being used on you at the time. So we think about that as a normal force. So in situations where you feel really light, your normal force is smaller. And in situations when you feel heavy, your normal force is greater. So one way to visualize this is imagine you've got a spring scale, and lucky you don't have to imagine. So if I've got a spring scale and a mass attached to it, you can see that obviously if I just sit there and I don't really do too much, then the spring scale is going to weigh the weight measured by the spring scale is equal to the supporting force, which is equal to the actual weight of the block or of the object. But in certain situations, if I accelerate one way or another, I can get that value to change. Now, as I move up and down, it's not the weight that's changing. This is still the same force of gravity. But there are times when this thing would feel extra heavy and times when it would feel kind of lighter than normal. And so what's happening in those situations? Well, if you could imagine if this was like an elevator and just moving up or down and only could move in those two directions, think about situations where you might feel extra heavy. Well, one of those would be if I was going down and I stopped suddenly. So if I'm traveling downwards and I stop suddenly, you can see this kind of bottoms out. So moving down, and stopping. Okay, so going downwards but stopping. But another way that I could feel extra heavy would be actually if I start on the ground floor and if all of a sudden I accelerate upwards. You can see in that brief instant, it's like stretching out like this. So I could be moving up and speeding up. Now, I'm purposely using not very physicsy language because I just want to think about this situation and think about what's happening in these situations. Now, same thing with the two times we're feeling lighter than usual. One time we could feel light is if I'm going upwards. So if I'm on my way upwards and then I come to a stop. So on my way upwards and I stop, you can see this is going to kind of boop up a little bit like this. So I could be moving upwards and stopping. And then the other possibility is maybe I'm on the top floor already, but then in that brief instant when I start to go downwards. So as I start off, you can see this is going to drop away like this. So I could be moving downwards. And speeding up. And then the three times, and I've given you two spaces there, but whatever. The times when it's not really changing. Well, so if I'm not moving, then my apparent weight is equal to my actual weight. So not moving. But that's actually not the only thing. I can be moving. I could be moving upwards or I could be moving downwards, but it's only if I'm moving up or down at a constant velocity. Moving up or down at a constant velocity. So let's think about all these situations. Let's think about what they have in common, because at first glance it can be a little bit misleading. You can't just assume that every time you go up in an elevator you're going to feel heavy, because you can see there's examples here where I'm moving upwards and speeding up I feel heavy, but if I'm moving upwards and stopping I feel light. So it's not about which way you're moving. Think of it in terms of, it's not about the direction of your velocity. Really, it's about the direction of change in your velocity, which we all know is an acceleration. So these two situations here, if I'm moving downwards and stopping, or moving upwards and getting faster, these are both examples where my acceleration is upward or positive, right? So in both of these examples, my acceleration is upwards, and so I feel extra heavy. In both of these examples here, where I'm moving upwards but coming to a stop, or I'm moving downwards faster and faster, these are both examples where the acceleration is downwards or negative. And so really, you can tell whether you're going to feel heavier or lighter based not which way you're going, but which way you're accelerating. If you're accelerating upwards, you feel extra heavy. If you're accelerating downwards, you're going to feel extra light, whatever that means. And of course, in both of these cases here, the acceleration is 0. And so if your acceleration is 0, even if you're moving, if you're not accelerating, then you are going to feel as heavy as you are. Your actual weight is going to match your apparent weight. So let's look at a few examples where we might solve this. So I've got a person in an elevator, okay, free body diagram time, traveling upwards at 5 meters per second. What is their apparent weight? So as they stand on this elevator, they've got a force of gravity pulling down on them, and I would have a normal force pushing up. And even though they're moving at a constant velocity. There's no acceleration there. So these two forces would be the same, okay? And remember, when I say apparent weight, really that is the normal force. So it's just asking what is their normal force. Well, in this case, the normal force would just equal the force of gravity, which would equal m times g, which is 65 times 9.8, which to 2 sig figs is going to work out to be about 640 newtons. Okay, let's try another example. Now in this case, this same person is now accelerating upwards at 4.9 meters per second squared. So what's their apparent weight? Now notice that compared to the first question, the force of gravity in the first and the second question are going to be exactly the same. That's still just equal to mg. So Fg equals mg. That hasn't changed. That's 640 newtons. So that's not going anywhere. But we're now accelerating upwards. So if we're accelerating upwards, then the normal force must be larger than the force of gravity. Otherwise, you wouldn't be able to accelerate upwards. If they're equal to each other, you're not accelerating. So what this is going to do is going to lead me to a net force equation. So for my net force in this case, I'm going to do winners minus losers. And since the upwards is the winning direction, I'm going to do Fn minus Fg equals ma. So solving for the normal force, Fn is going to equal Fg plus ma. Now I already know the weight from before, the Fg from before, so that's 640 plus 65 times 4.9. These boxes are too small. And I get an answer of right around 960 newtons for that one, okay? And last but not least, I've got the elevator is now accelerating. Well, it reaches the top floor and decelerates. So it's going upwards and slowing down, which means the acceleration is downwards. And so again, the weight, the Fg is the exact same as it always was. That's not changing. But in this case, the normal force is going to be smaller than previously. And so in this case, when I come up with the net force equation, I'm going to use the winning direction as being down. So I'm going to say it's actually Fg minus Fn equals ma. And so the normal force is going to equal the difference between Fg and ma. So that's 640 minus 65 times 4.9, and this ends up being right around 320 newtons. Okay, So again, the take-home message with this is you first just have to identify which way it's accelerating. The direction that it accelerates is going to change your equation. There isn't one equation you can use to find the normal force, because you have to first kind of figure out, is the normal force a winner or a loser? Okay, so last question. An 85 kilogram person in an elevator goes from the top floor to the bottom floor. Find their apparent weight when they accelerate from rest at a rate of 3 meters per second squared. So they're on the top floor and they're going downwards. Okay, so I'm just going to make a note. Don't usually write accelerations in my free body diagram, but I just want to point out that the acceleration is downwards, or accelerating from rest downwards, which means my force of gravity is a certain length. And if I'm accelerating downwards, then the normal force has to be smaller than the force of gravity. So I'm going to create my F net equation. F net equals winner, gravity, minus loser, normal force, equals ma. And then solving for Fn, Fn is going to equal Fg minus ma. Now I didn't solve gravity yet, but I can just plug in m and g. So I get 85 times 9.8 minus 85 times 3. And I realize now I could have just collected my like terms, but I've come this far, so too bad. And the final answer ends up being right around 578 newtons. I guess I'm good to 3 sig figs on this one. Okay, so that is it for elevator problems.